Okay, so we're going to have a new chapter today, the gas state. So we already discussed the three physical state at the beginning of the semester. So we have the solid, liquid, and gas. And we say the way that we're going to differentiating them is volume and what's the other one? Shape.
Shape.
Okay. So these are both definite shape, uh, definite volume, but not definite shape. And this one, no definite volume and no definite shape. Okay. So that's what we have learned about gases at the beginning of the semester. We also say that they are compressible. So when you say compressible, because there's big space in between them, you can accommodate some of the gas molecules or atoms in between, allowing them to be able to be compressed. So when you say compress, you can minimize the volume, okay, because you can fit gas molecules or atoms in between gas molecules and atoms. And if we're going to look at some of the other physical states of these gases, we can also say that they're usually expand to fill their containers. Okay, like the balloons. Where's that balloons that I have here? My daughter was playing with it earlier. And the good thing about these gases, when you mix them, you always form what? A hetero or homogeneous mixture.
Homogeneous.
Okay, it's always a homogeneous mixture. So you mix a colorless with a colorless gases, you end up with a colorless gas mixture. You mix a brown and a colorless. The brown is the only one that you will see. Okay, and in addition to that, if you're going to look at the density, so the way that you look density in the solid, it is what grams per kilograms, grams per ml. Okay, or not grams per kilogram, but grams in cubic centimeter. That's for solid. For liquid is grams per ml. But for the gases, it's grams per liters. So as you could see here, the gas density is really low compared to the other, what we call density. Now, what they found out that all gases can be characterized by pressure, volume, temperature, and the amount of gases. And they also found out that these four, we could say, properties are related in such a way that if you have three of them, you can determine the fourth one. Okay? So we're going to discuss these four characteristics or properties and how by studying these characteristics and properties they were able to come up with some laws. I don't know if you can call it odd, okay, but among the three physical state, gases is the one that has the most number of natural laws, and you're going to learn some of them today. So if you're going to look at the natural laws for the three physical state, I can say that the gases has the most number. So you just add that something that you cannot see, but you can feel, okay, has the most number of natural laws. It only means that it is the most studied physical state. Okay? So we start first with our definition of pressure. So maybe right now, all of you are from David Bowie's and Queen songs titled Under Pressure, right? So the term under pressure is, I would say, correct in its aspect, because if you're going to look at the definition of pressure, that's the force exerted per unit area. Okay, so that's the one that you have if you are in a particular place. So solid don't have this pressure. They might have, but it's so little. Liquid don't have it, but at least the gas exhibited this property of what we call the pressure. Okay, so it's one thing that you will know if you have what we call the gases, because these are properties that define the state of a gas sample. So if you're going to look at the pressure, you might encounter the term atmospheric pressure. So atmospheric pressure is just the weight of air per unit area. Okay? So I would ask yourself, what do you think the effect of pressure on the height? Okay? So let's say this is a mountain. You're here, and compare it in the situations that you're here. How can you say the difference in terms of pressure? Which is a higher pressure? If I'm going to ask you here P1 versus P2.
You'll have higher
P1.
pressure at
Okay?
P1 than
So the
P2.
one that is higher pressure is,
P1.
how are we going to do the relationship here? Like that. Because as I told you, our definition here, force exerted per unit area. And if you're going to look at the other definition of pressure, you end up with this one. Okay? So density times gravity times height. So we say we have a greater pressure at low, how do you call that? Elevation. At higher elevation, the pressure is less. That's why what happened, if you go over a peak, you have a hard time breathing because you don't have enough air in that area. If you go to Mount Everest, you have to supply your own oxygen tank because the air on top of that thing is really thin because of low pressure. Okay? Now, the SI unit for pressure is Pascal, which is PA. But you don't usually use that. So if you're going to look at Pascal, the definition of that is equals to kilogram times meter over S squared per meter squared, which when you simplify will be equals to what? Kilogram times meter S squared. Okay, so this is the unit for Pascal. So you could say, so this is how you derive from here. So force is equals to kilogram times meters per second squared. So what is usually the unit of force? Anyone? It's after the name of the person.
Newton.
Newtons.
Okay, it's Newton. So Newton is kilogram times meters over second squared. So area is meters squared. Okay, so how do we do it in terms of this definition here? Pressure is equals to density times gravity, okay, times height. So if you're going to look at density, so we could say kilogram meter, not squared, but cube, okay, because that's a volume. And then the acceleration due to the gravity meters per second squared, and you have the height, which is equals to meters. So if you're going to do the calculation here, you end up also with the same unit as this, just showing you that the two are related. Okay. Now, although Pascal is the SI unit, we don't usually use it. Commonly, the one that we use is ATM. Not at the moment, okay? But atmosphere. Another thing that they use is millimeter mercury. In some, they use torr, and other they use bar. So if you're going to look at the equivalence of this with one unit and the other, Pascal, which is the original one, so 1 atmosphere, which is ATM, that's equivalent to 1.01 times 10 to the 5 Pascal, or 101 kilopascal. Now, the original unit that they have for pressure is millimeter mercury. Why do you think it's millimeter mercury? Okay, we will know about it as we go on. So millimeter mercury is defined as 760 millimeter mercury, and that is equals to 1 atmosphere. And they also call this millimeter mercury as torr. Again, I'll tell you the story as we go on. Now, others would have it as 1.01325 bar as equals to 1 atmosphere. So if you're going to look at this, the bar is just equivalent to your Pascal, right? 1 ATM, we could say 1 bar is just equals to what? This value that we have there. So instead of saying 101 kilopascal, if you convert it to a bar, that is equivalent to 1.01325 bar. Okay? So these are the units that they usually use. And the one that is commonly used is ATM, the atmosphere. So there are two devices that's used to measure pressure. One is the barometer, okay? And the other one is a manometer. So the difference between the two, one is you measure it, the pressure of the atmosphere, while the other one you measure the pressure of a gas or liquid in a vessel. Okay, so here how the story that we have on how we end up with 760 millimeter mercury. So the setup that they have during that time, so there's a guy by the name of Evangelista Torricelli. So he's studying gases. So to measure the pressure of the gases, he had a device similar to this one. And what he did, he put there mercury. Now, when he tried to measure the atmospheric pressure, he looked at the height of the mercury in his capillary, and he found out it's 760 millimeter or 76 centimeter. So that's how we end up with this value of 760 millimeter mercury. That's the height of the mercury in atmospheric pressure. Okay? Now, what do you think happened if instead of mercury, you're going to use water? Which do you think would have a higher column? So what if we're going to replace mercury with water? Okay, so which of the barometers would have a higher column of the liquid? So usually, the answer that we have there, the water column would be higher. Why? Because the density of the water is less than the density of the mercury. Mercury is what? 13 times denser than water. So we could say the height of the water will be 13 times more compared to the height of the mercury. But this is the story how we end up with 760 millimeter mercury and the Thor, which is just in honor of Evangelista Torresili. Okay? Now, the study of gases is one of the earliest scientific methods, or one of the earliest event where scientific method was applied. Okay? So we could say here, this is the start of the so-called empirical gas law. So the way that they look at this empirical gas law, so I mentioned to you the four properties that gases has. So what they did, they study two of them at a time, while the other two are, we could say, constant. And they look at what's happening. Okay? And this study led to the empirical gas law that's occurred from the mid-17th century until the mid-19th century. And the first one who did it is by the guy named Robert Boyle, the author of one of the first thing that follow the scientific method, skeptical chemist. So what did Robert Boyle did? He looked at the relationship between pressure and volume at constant temperature. Okay? So he found out that the volume of a sample of gas at constant temperature varies inversely with the applied pressure. So what he found out is there is an indirect relationship between pressure and volume. As he increased the pressure, okay, the volume decreases, or vice versa. Okay? So this is the mathematical relationship that he found out. And if we're going to look at the product of pressure with volume, it will give you a constant, which would tell you that if you, okay, know the initial volume and pressure, you should be able to tell also either the final pressure or volume if one of them is given. Okay, so if we're going to look at this, when he plotted the relationship that we have, so you end up with this one. So what can you say about this one? They are inversely proportional, but the problem is they are nonlinear. Okay, so to make it linear, instead of plotting volume, what he did is he plot the reciprocal of volume, 1 over B. And from that, he was able to get a linear plot. Okay, but the plot is only linear. The relationship is inverse because he converted the volume to its reciprocal. Okay, so the way that he did here, if we're going to look at the real life example for the relationship of pressure with volume, I think this is one of them. So you have here a J tube. So what the J tube this is a closed seal, and this is an open, what we call the hole. So you always entrap your gases in this one. So what happened? If you're going to add liquid, you're adding pressure. Now, if you add the liquid, the added pressure will cause the volume to decrease. So for instance here, this is the normal pressure. Okay, so what happened? If you add the pressure and make it 760 millimeters, so from 100 ml, it becomes 50 ml. When you double the pressure here, 760, okay, what happened? So this is triple the pressure now. Okay, because this is the one that you double. So you triple it. So what happened? The size that you have is 1/3 of the original one, which is 100 ml. So this is an example on how volume is affected by the added pressure. Okay. Remember when you have a syringe, what do you need to make the volume small? You apply pressure. Okay, and there's a time even if you apply too much pressure, the volume of the syringe don't change. And sometimes when the pressure is too much, what will happen? Your syringe just pop out because the pressure that you apply is enough to push whatever's what we call preventing it from escaping. You can also apply this concept in this cylinder. So this is most of the thing that we're going to do both in this chapter 5 and chapter 6. So it mentioned here when 1 gram of oxygen gas at 0 degrees Celsius is placed in a container at the pressure of 0.5 atmosphere, it occupies a volume of 1.4 liter. So when the pressure on the oxygen is doubled to 1 atmosphere, the volume is reduced to 0.70 liter, half the original volume. Okay, so you have here 0.5, and initially you have 1.4. So you double this one. What happened to the new volume? 1/2 of the original, right? So let's try to have some problem. So a volume of the oxygen gas occupies 38.7 ml at 751 millimeter mercury and 21 degrees Celsius. So what is the volume if the pressure changes to 359 millimeter mercury while the temperature remains constant? So how are we going to solve this? So the way I solve this one, first, I list down maybe the initial volume. So I have here 38.7 ml. And then the initial pressure, 751 millimeter mercury. And then what do we have? What is this 359 millimeter mercury? That's your final pressure. And you are asked for the final volume. Now, before we solve this, can you guess what will be the final volume based on the final pressure? Will the final volume be equal, less, or more than 38.7?
Less.
Okay, so as you could see here, is it less? So 38.7, 751. So what will happen? From this, the pressure went down. So what do you think happened with the volume? Okay. So what do you think the volume?
It goes up.
The volume went up.
Go down.
Increase.
Volume increases.
So this goes down. So that means this should go up. Then to see, P1B1 equals to P2B2. And divide both sides by P2. And then replace it 38.7 ml times 751 millimeter mercury, and then divided by 359 millimeter mercury. So do it there. So what's the number that you get?
90 ml. I mean, 81 ml.
Okay. So if you're going to follow the calculation, how many significant figures do we have?
3.
Okay, so it would be equals to what?
It would still be 81 because it's 80.95.
So if it's 80.9, you have to write the whole thing. Is that the answer? So as you could see, 80.9 is greater than 38.7. So if it's 80.95 that you get there, you can run it up to 81.0. Okay. So you got this. So this is just a simple calculation. And this is the first natural law on gases. The first empirical gas law. Now the second one came maybe around 100 years or more after. Okay, so this is a French guy by the name of Jacques Charles. So what he did is he plot volume versus temperature. So he looked at the relationship of volume versus temperature. And he found out, okay, that if you're going to plot any gases, okay, there will come a time that all of them will meet at a certain temperature. So a graph of the volume versus temperature, he found it to be linear, and all of these linear lines cross zero volume at the same temperature, which is negative 273.15. And from that temperature was designated as absolute zero. So this is the temperature at which the volume of the gas is hypothetically zero. And that absolute scale became known as your Kelvin scale. Okay? So this thing was observed by Jacques Charles. Wherein he looked at the relationship of two properties at constant pressure. So he found out volume is directly proportional to temperature. So what does it mean? Okay, as the temperature increases, the volume also increases. And if you're going to put it in an equation form, this is what you have. So remember, the earlier that we have here, this one, P and B, they are indirectly proportional. But if you have it like this one, you have a relationship that is directly proportional. So that becomes your Charles law. So if you want direct evidence on how temperature affects the volume, this is what you have. So what happened here? So you have this balloon that was immersed in the liquid nitrogen. And when you remove it, okay, the balloon expands. So what could be the explanation there? It has something to do on how the molecules or atoms of gases are close to one another. So you could say at lower temperature, they are very close to one another. But as you increase the temperature, okay, what happened? They start moving, so they become far from one another. So that's the explanation that they have there for the expansion that you observe in gases when you increase their temperature. Okay? Now, if you're going to look at this as piston scale, so as you could see here, the pressure is the same. Okay? But what's the one that's changing? The temperature and how it changes in terms of the volume. So initially you have your 100 Kelvin. So you have a volume of 0.26. So look what happened if you put it in 200 Kelvin. Look at the volume. So what do you think happened?
The temperature increased?
Yes, the temperature increased. So what happened when the temperature increased? What happened to the molecules?
It increased as well.
So when the temperature increases, what happened? The molecule starts to move. Temperature is just the kinetic energy of the molecules. Okay? So when you say 200 Kelvin, that means your molecules are already moving there. So there is more energy at 200 Kelvin compared to 100 Kelvin. So remember, I told you, temperature is just a measurement of the kinetic energies of the molecules. So how can you increase your kinetic energy? You go to the definition of kinetic energy. Kinetic energy is energy in motion. Okay, so at this temperature, since the molecule starts to move, they start expanding. And when they start expanding, their volume increases. So what happened here? You double the temperature, you also double the volume. So that's Charles' law. Okay, and again, we have an example on that. So if you're going to look at the example that we have here, you prepared carbon dioxide by adding hydrochloric acid to marble chips calcium carbonate. According to your calculations, you should obtain 79.4 ml of carbon dioxide at 0 degrees Celsius and 760 millimeter mercury. How many ml of gas would you obtain at 27 degrees Celsius? So if we're going to look at the problem here, we can have a B1 that's 79.2 ml, a T1 that is 0 degrees Celsius. And then you have B2 that you don't know, and you have T2 that is 27 degrees Celsius. Now, this is the thing. You have to be very careful with the temperature. Okay? Temperature, what you do is you need to convert it to what?
Kelvin?
Absolute scale.
It's
Why
7.
do you think you have to do that? Why do you think you need to do that?
Because then we would divide by 0.
Is it the 0 only? What will happen if you don't what we call the convert it to Kelvin? you might end up with a negative value. And it doesn't make sense if you have a negative value. Okay? Because the zero that you have here, it can go down to what? -1 until -273.15. So you want to use the absolute scale. So how do you do the absolute scale? Convert this to Kelvin. So 0 degrees Celsius is equals to what? 273 Kelvin, if you recall your chapter 1. And 27 degrees Celsius is, when you convert it, around 300 Kelvin. So that's the thing that you need to remember. And it's in all gas calculation, not only Charles law. Whenever you are asked for any gas calculation, make sure that the unit of temperature is in Kelvin. Okay? So when we have that, we can rearrange this one. So we know B1 equals to T1 equals to B2 over T2. And what do we need? This one. So we cross multiply B1 times T2 over T1. So that's equals to B2. So you convert the one that you have there, you use the values that you have, so ml, and then T2 is 300K, and then T1 is what? $273K. So if you're going to look at the unit, you cancel this one, you end up with ml. So before you answer, what do you think will be the value of your volume here? Is it lower or higher than 79.4?
You have to know how to do it. You have to know how to go in class.
Higher.
Try to calculate it. I'll be back. So what do you get? How do you change Celsius to Kelvin? Anyone? You took it in your first exam.
Don't you just add 273?
So you add whatever the Celsius to 273.
Can we say what we got?
So this would be equals to what?
87.3.
Okay, 87.3. Okay. So does that number make sense? So 273 increased to 300, so you expect 79.4 to also increase. And 87.3 is greater than 79.4. Question. Question? So what do we do next is we combine the two laws. So we say In the Boyle's law, we have it like this. In the Charles law, we have it like this. So when you combine them, we end up like that one. So that's, we could say, a combined gas law. So if you're going to look at the combined gas law, you just combine the statement of the two gas law. So the volume of the gas at constant pressure is inversely proportional to the pressure and directly proportional to the absolute temperature. And what you do is you end up with this relationship of the initial and the final condition of gases. So here, you have to take into consideration now what is happening when you have a new volume, a new temperature, and a new pressure. Can you predict it? Not really, because one is that has a direct relationship like temperature and volume, and the other one like pressure and volume, they have an indirect relationship. So let's try to apply it here. So divers from North Sea drilling's platform experience pressure of 5.0 times 10 to the 1 atmosphere at a depth of 5.0 times 10 to the 2 meter. If a balloon is inflated to a volume of 5 liter, which is equivalent to the volume of our lung, at that depth at a water temperature of 4 degrees Celsius, what would be the volume of the balloon be on the surface, which has a 1 atmosphere pressure and a temperature of 11 degrees Celsius? So how are we going to analyze this problem? So we go putting down the information that's given, B1, P1, T1, and then the corresponding B2, P2, T2. So we can put B1 as 5 liter. What is pressure? What would be P1?
1.
Would it be the
One?
5 times 10 to the second thingy?
I think it's this one. Five point zero times 10 to the 1 atmosphere. And what's the temperature, the initial temperature? Anyone?
4 Celsius.
4 degrees Celsius, which is equals now to 277 K. Anyone has a problem where I got the 277 K? I convert the Celsius to Kelvin. So my B2 now would be the one that I'm looking for, right? My P2 is 1 atmosphere. And the temperature that I have 11 degrees Celsius, so that is
284 Kelvin.
how much Kelvin?
284.
284 Kelvin. And what I'm going to do now, remember I have the relationship PB over T, so 111, P2 B2 over T2. What I'm looking for, this one. So I put everything there, P1 B1 T2 over P1 P2 equals to B2. And then I'm just going to put all the values that I have placed here. So pressure 1 is 5 times 10 to the 1. volume would be 5 liter, temperature would be 284 Kelvin divided by 77 Kelvin, and what's the other one? 1 atmosphere. So if we're going to look at the unit, Kelvin, Kelvin out, atmosphere out, so you have the liters, which is a unit of volume. So what do you get?
$256.3.
Hmm?
256.
So you get there around 260. I have to put it into decimal places following the significant figures rule. Because you get what? 256, right?
Yes.
So I have to what we call write it into significant figures. So how do I write 256 in two significant figures? I put it around it up to 2.6 times 10 to the 2. That's 260. You don't need to convert anything because they will just cancel out. So you just doing additional step that's not even necessary.
Would 26 times 10 also be valid? Would 26 times 10 to the first be valid as well?
No, because the rule of these significant figures is you have a number from 1 to 9.9 as much
okay.
as possible. That's the scientific notation that we follow. So this is the combined gas law. But as you could see, we only discussed 3 of the characteristics or properties of gases. We said there's 4. Okay. So the 4th one has something to do with the amount, or indirectly here mentioned as the number of molecules. So who else studied the number of molecules then? The guy who devised the mole concept, Amadeo Avogadro. So what does Avogadro's laws mean? Equal volume of any 2 gases at the same temperature and pressure contain the same number of molecules. Okay, so if you have a temperature and pressure that are the same, that means the moles, or the number, not really the moles, let's just say number of molecules are also the same. So if we're going to look at this, where's the volume? Okay, so you can incorporate the volume there with the number of the molecules. Because the way that they look at this, when they replace this at standard temperature and pressure. So when you say standard temperature and pressure, that's equivalent to 0 degrees Celsius and 1 atmosphere pressure. You're going to have a molar volume that is equal to 22.4 liter per mole. So what does it mean? If the pressure and the temperature are at the standard value, the volume of your gas is equals to 22.4 liters. And that corresponds to 1 mole of any gases. That's why the concept that they have here is molar volume. So that's the volume in 1 mole. And you can see here liters per mole. So if it's at 0 and 1 atmosphere, the corresponding value for that is 22.4. How big is 22.4? A little bit bigger than the basketball. Okay, so how are we going to relate the moles? Because we already have your what? PB, B or T. So where do we put the moles? Where do we put the number of moles? Before we go with the PB and RT, how would be the relationship maybe of the volume with respect to moles? Can we say as what would be the relationship of that? Would it be like this or like this?
The second option.
Okay. So if we're going to look at this, we can say that volume is directly proportional to the number of moles. Now let's see if that's the right one. So if we have it like this, PB, okay, N of T, they said it will give you a constant. Why does it give you a constant? Because these are the 4 properties that you can see in gases. So it gives you a constant. Okay. So once you know the P, the volume, the N, and the T of a given gas, it will give you to a particular constant. And that's the basis of your so-called ideal gas law. So remember, it came from here. So when I rearrange it, I just cross multiply it there. So I end up with PV equals to nRT. Try to convince yourself that they're the same. So what is the ideal gas law? That's the one that put the 4 properties or characteristic of the gases. The ideal gas law will let you know the 4th property or characteristic if the 3 others are given. And R represents as what we call the ideal gas constant. And his value is this. But we're going to focus either with this one or with this one. And it will be given to you. Now, you may ask yourself, when are we going to do this one, use this one, and when are we going to use this one? We use the second one when energy is related or energy related problems. For this one, That's the non-energetic energy problem, non-energy problem or energetic problem. Now you may ask yourself, how do we know if it's energy? That one. Because energy is usually a unit of what? What's the unit that we use for energy? Anyone?
Joules.
Joules. That's why you have that. So whenever you have the 8.314 joules per kmol, that means you only use it if there's an energetic problem. Now for non-energetic problem, you use the 0.08205 or 0.0821, as some other books would say it. Okay. Now, if you're going to look at this molar gas constant that we know as R, which is now our ideal gas constant, you could say that it's a constant of proportionality that relates the molar volume of a gas to temperature and pressure. And if you go further, okay, you can put varying amounts of a gas into a given container at a given temperature, and then you can use the ideal gas law to show that the amount of gas is proportional to the temperature at constant temperature and volume. So if we're going to relate here pressure with what we call the N, remember we have a relationship of B over N, right? So the question now is, how are these two related? Will it be like this, or will it be like this one? What's your answer? Is it the first one or the second one?
The second.
Okay, it's the second one. And I have another way of saying it here. So as you could see there, this is a constant. N is related to P. Just like volume is related to T. Or volume is related to N also. And if you're going to look at the ideal gas law, you see it like that, right? It's just the same as this. P1, B1, N1, and T1, P2, B2, N2, T2. So what does this tells us? This tells us that we can derive the other gas laws that we have discussed already from here. How? So when we derive Boyle's law, what's the constant properties that you have there? Isn't it the temperature and the moles of the gas? Because what happened here, they have the same value. So if they have the same value, that's just equals to what? If you divide them, what's the number that you get if you have the same value and you divide them? Anyone?
One.
Huh? Destiny? You said something.
Is it one if you
Yeah,
divide?
it's one. Right? So how can we derive the Boyle's law? All you need to do, what's the properties that you relate? Pressure and volume. So the other will have the same. So if you're going to combine them, this N1 and T1, if you cross multiply it, it will just be what? N2T2 over N1T1. Since the value are the same, they're just 1. So you're left with what? P1B1 equals to P2B2. Does that make sense? Anyone? Because what I'm trying to show you here, using this equation here, you can derive what we have discussed so far. For instance, Charles' law. So in Charles' law, what are the one that's constant? Charles' law looks at B1 and P1, right? So the one that's constant is P1 and N1. So if you cross multiply P1 times N2 divided by P2 times N1, you just get 1, leaving you with the equation of B1 over T1 equals to B2 over T2. So if you want the Boyle's law, you remove this, right? And what you have, there's the Boyle's law. If you want the what we call Charles' law, you remove this. They're just the same. So you end up with B1 over T1 equals to B2 over T2. Because in the exam, what you're going to be given is just PB equals to nRT. But you know, each of these will give you what? R. Because they are constant. Does that make sense? Because I don't want any comments. I have to teach myself. Because all I can say is I can explain it to you, but I cannot make it understand for your behalf, in your behalf.
I have a question.
Okay.
So does R, like you put the R over the P, so sometimes does R just replace the P?
No, if you're going to look at this, okay. So this is where the R came from.
Okay.
Because R is a constant. So if you're going to change the condition there, it will still give you this.
R.
So that means I can connect this with this one. That's what we have there.
Okay, and they'll both be R. Okay.
What we did, I discussed to you the empirical gas law, and then from that we end up with the ideal gas equation. But what I'm trying to show now, we have an ideal gas equation wherein we can derive the other empirical gas law.
Okay. It's slowly connecting. Slowly.
Okay, so R is a constant. It's either the 8.314 or 0.0831 or 0.0821 or 0.0205 something that was written here. But what I'm telling you is in the exam, this is all that you're going to be given. So it's up to you to derive the Boyle's law, the Charles law. And this is why what I'm showing it to you. So what you're going to do is you isolate R. So when you isolate R, what happened? You divide both sides by NT. And you know R is always a constant. Okay? Now, let's try to solve a problem using the ideal gas equation. And then later on, we'll do some derivatives out of this ideal gas equation. So a 50-liter cylinder of nitrogen has a pressure of 17.1 atmosphere at 22 degrees Celsius. So what is the mass of nitrogen in the cylinder? So all you need to do is, what is this one? That's your B, right? How about this one? What is this?
P.
That's your P. And this one?
Temperature.
That's your temperature, but you need to convert it to K. So the one that's being asked is mass of the nitrogen. So you go back here. So you ask yourself, which are the one that is accounted for already? You say this one, R is always given, and this one. So you're going to go for this. So you can rearrange it in such a way that you leave N on one side. So that will be like this. Everybody get the math here? So if you're going to do the math here, I just divide both sides by RT. And then what I'm going to do, I'm going to replace it with the one that I have there. So this is 17.1 atmosphere. And I have 50 liters. And then I can use, this is a non-energetic problem, so I can use the 820, so 8205, 82058, so 8206 liter atmosphere K mole. And then this is equals to what, Kelvin? 273 plus 23, is that 296?
Yes.
So if you're going to look at the units, you can cancel out the one that you can cancel out. So the unit that you have is mole. So what moles? How many moles do we have?
35.6.
35.2.
6. I got 0.6.
0.6?
I got
I have
0.2.
0.2.
The one that I have in my thing is 352, 35.2. So let's say 35.2, just. So are we done?
No.
Are we
No.
done?
Now you need to convert it to
No,
grams.
because what we are asked is the mass. What we have is the moles. So all we need to do is multiply it with what? For every 1 mole, the molar mass of nitrogen. So usually it's N2, so this will be 28.02 grams. And then we're going to be done. What do you get?
$986.3.
Okay. No, we can end up with that one. So this is the long way. You may ask, can we have a shortcut? Yes, I can derive something from here. What's the definition of N? What is N here? Anyone?
Moles.
Moles. So what is the moles equal to? Moles is equals to mass over the molar mass. So I can put it like this, right? So which one do I need? So that means I can incorporate this here. So that means I can always put here the 28.02 grams per mole. So if you're going to look at the unit, it cancel the moles, and I will still end up with this number. So what I have here, M is equals to PB times molar mass over RT, which is just already just the same thing as this one. Analyze. So question here. Before we go on some other modification using PB equals to nRT. So if you're going to look at this from this one, we try to derive an equation wherein we get for the mass, or we can get for the molar mass. So we end up with this one. So if we have for the molar mass, it will be molar mass equals to PB. How do we do it if it's this one? So we move that thing there, and then we have so this is where it went, right? Because you multiply both sides by mm. So what will happen? We want to isolate this one. So we need to multiply both sides by RT over PB. And when that happens, you have MRT over PP. So that's just the derivative that you can do using PP and RT. And I'm going to continue that here. Okay. So using the ideal gas law, it is possible to calculate the moles in 1 liter at a given temperature and pressure. The number of liters can then be converted to grams per liter. And to find the molar mass, you find the moles of the gas and then find the ratio of mass to moles. And then in equation form, this is what we have. Okay, so we end up in the previous slide, molar mass is equals to MRT over PB, right? Or the other one, mass equals to PB, molar mass RT. So the question now is, how do we relate the molar mass that we have with density? How do we define density? Anyone? How do we define density?
Mass over volume.
So it's mass over volume. So if you're going to look at this, so we have a molar mass here. So we have a mass here and da-da-da. So M over V here will be your density. So what will happen? Your molar mass now is equals to dRT over P, which is this one. Make sense? Now, how do we isolate this on one side? So we cross multiply each side with P over RT. And we end up with density equals to P molar mass over RT, which is this one. So let's try to solve our last problem for today. So what is the density of methane gas that has a formula of CH4 at 125 degrees Celsius and 3.5 atmosphere? So maybe we can go right away with this formula that we have here. This D M P RT. Right? So where will I get the molar mass?
CH4,
CH4. So that is equals to
16.04.
16.04 grams per mole. And then pressure is given here as 3.50 atmosphere. And then I have here 0.08206 liter atmosphere K mole. And the temperature that I have here, again, you have to convert to Kelvin. So that is equals to what?
398.
398 Kelvin. So if you're going to look at the unit, I cancel the one that I can cancel, atmosphere, atmosphere, moles, moles, Kelvin, Kelvin, and I end up with grams per liter, which is a unit of density. So what do you get?
$1.72.
Okay. $1.72. That's enough, Megan. That's enough. That's enough. You're going to overflow it again. Are you done with class? Are you done?
Yes.
Okay.
I'm going back.
Question. So question.